Professor Kubusue, to take our lecture 4. So in the classroom, and it would be nice if you can follow, so that when we get to the hands-on, you'll be able to attend it on your own. However, as we continue, if you have any questions or issues, let me know. So today's lecture is on neural network and neural language models. This lecture is going to be in 2 parts. Today's lecture is the first part, the first of the 2 parts. So what are the objectives for today? First, we expect that at the end of today's lecture, each one of us will have an understanding of the basics of artificial neural networks, also known as ANNs. Then we will have understood to a certain level the concept of feedforward network and its counterpart, which is backpropagation. Then we'll learn how neural language models and word embeddings helps to improve text processing. Finally, we implement our word embeddings in Google Colab. Okay, so it means that we'll be using Python programming language. So let's begin with an introduction to neural networks. Before I go on, let me go back to the class and have an idea of our participants. Okay, good. That's great. So, when you think of neural network, you should think of it as the brain of the computer, otherwise known as the brain of your machine. Just as humans have neurons, and in terms of the brain, there are billions of neurons. Here we are talking about a replica of that brain in your computer or machine. So we say that a neural network is a system that learns patterns from data and goes on to make predictions. If you were in our very first class, you'll recall that when we were describing machine learning, we talked about machines that are able to learn from data. So here, neural network is like mimicking the human neurons. Biological neurons belong to humans. But now, for computers or your machines, what you have is neural network. The summary is that when you hear neural network, what should come to your mind is a brain for machines. And this is very important because it has been used widely in machine learning, in AI, in deep learning. So if we want to recall some of the things that we have seen in our earlier lectures, you remember that we talked about AI as the umbrella name, and that within AI, we have several other concepts, one of which is what we are looking at today. Because we are linguists in this class, and our program is on linguistics, we are not going to be focusing on the other various areas where neural network can be applied. Instead, we'll be focusing on the ones that are related to language. Okay, so linguistic, language, and all that, they are all interrelated. So when we say real world uses in NLP, it is because we are focusing on language, linguistics, and all of that. Some examples are spam detection. So by adopting this neural network approach, it is possible to filter your, messages, your email messages, your Gmail messages, so that you can distinguish between mails that are potentially spam and those that are likely to be harmful. So, we talked about that also at the earlier part of our lectures. A mail can be spam and can be harmed. By using machine learning techniques, you can predict whether it is PAM or ARM. Today we are saying that the application that we talked about earlier, we could also do the same thing with neural network. The other thing that we can, achieve is sentiment analysis. For instance, when people read a novel or watch a film or buy an item, okay, but in this example, we're looking at movie reviews. You can use neural network and apply it to know people's opinion about the movie, for instance, whether they are positively, biased towards it, such that when they review, they'll give positive comments or choose values that are high enough to show that they love the video or otherwise. Again, neural networks are found used in chatbots. When you have your conversational systems where you can ask questions and receive responses. And this one is very common, in our time. Okay, so you have this Siri and Alexia, and then ChatGPT and so many other large language models, a lot of them. Finally, the fourth application that we are looking at here is in machine translation. That is using your computer to translate from one human language to another. Okay, don't forget that we have computer languages too. R and Python are two examples. But when we say machine translation, we are saying using our machine, that's computer, to translate from, say, English to French or German to Yoruba and stuff like that. An example is the Google Translate. And I guess that nearly everybody here must have used that for translation, one time or the other. So how does a neural network look like? So what we are going to do is we are going to go online and just show you so that by the time we begin to look at that note to make, neural network images. We'll look for a simplified one, okay? So we'll go to images. And then maybe we'll take this one. So you see that there are three distinct layers. I hope you can see my screen. There is the input layer, and then we have the hidden layer. Sometimes this hidden layer could be so many. In this example here, you see that we have the input layer in green, the hidden layers or middle layer, and then the output layer. This is the general structure of your neural network. Okay. So if we go back to our PDF, we will see that there are three main layers. One is the input layer. In this input layer, you take in features, text, the message. Okay, that's the input. And then the processing takes place in the middle layers. Take note that this layer could be one and it could be several. But at the end of the day, what you expect is the output layer. So for instance, if you are using a translation model or a translation, process, so you input text in, say, German, and then you have hidden layers where the processing takes place. And what happens there? That is when your network begins to learn the patterns. Okay, a lot of things happen there. If we go back to our image, you will see that there are, when you say network, then it actually shows up what you mean by network. Several connections between, different nodes, different points. And I said this one is a simple one that, gives us an idea of what we are talking about. Moving forward, your goal is to produce a final prediction. So say a sentence in English, I love rice, and you want an output in Yoruba. Okay? So there are hidden layers where the network begins to learn, from experience. By performing tasks and repeating those tasks, is able to, as you are going to see in the examples that we will see later on in our lecture. So don't forget there is the input layer, there are hidden layers, and then the output layers where you get your final prediction. Remember that is a prediction. And the beautiful thing about neural networks is that as they predict, they get better if they are, rewarded for performing well. Okay, so they learn better with time. So an example is here. This one is more like an example from sentiment analysis. So the input is, this movie is amazing. So the hidden layer will now learn from previous reviews how there might have been other reviews with similar words, sometimes exact sentences or phrases. So it learns the patterns. Maybe it realizes that every time I see amazing, it looks as if the things there are always towards positive. Okay, maybe amazing itself is clearly a positive, bias statement, but the movie itself being associated with that word is something that the network has to learn. And in this particular example, it's obvious that the sentiment this person is expressing is a positive one. Therefore, it's important for us to also know that when you are evaluating neural network, it's important for you to have somebody who has expertise in that domain. Okay, so that at the end of the day, that person could serve as a quality control to see if the outputs that are produced are human-like. Let's proceed. So don't forget, the example here is the movie is amazing, and then it learns from it, and then we see that the output is positive. So let's go, Kasaba.
Yes, sir.
How far? So far? How far so far?
I'm with you, sir. Yes, we are getting it, sir. I'm getting it, sir.
Okay, on behalf of the others, let's go to our class captain. Udo. Okay, Deborah, I'll come back to you. Udo. Hello, Udo.
Yes, sir. Good
How's it
afternoon,
going?
sir.
How's it going so far?
Yes. I'm following, sir. It's okay, sir.
How many layers do we have in neural networks?
Oh, we have three layers, sir.
What are they?
Okay, so I'm trying to bring out the. Hello, sir. Can you hear me?
I can hear you. Go on. Tell us the 3 layers.
Okay, we have the input layer where
Brilliant.
we also have the hidden layers that the neural network learns the patterns, and we also have the output layers which serve the final prediction, sir.
Fantastic. Deborah, you want to say something?
Yes, sir. Sorry, sir. My name is Lawal Kolaole. I'm actually joining, my device is dead, so I'm actually joining from a friend's device also. So I wanted
I'm here
to
to
ask.
Yeah, Deborah is dead. Yeah,
I'm here, okay.
Go on.
Yes, sir. So I wanted to ask, does that mean under the hood of every of these classifiers we looked at previously, like naive Bayes and others, does that mean under the hood there's a neural network working?
Okay, so I think you were not in our very first class that I had physically. So what we did was in that class we did something like DS, ML, AI, TL, NLP, ANN, and we said image, something like this. I hope you can see my screen.
We can, yes, sir.
Yeah. So DS means data science, machine learning, artificial intelligence, deep learning, natural language processing, and artificial neural network. And we're trying to say that there's a way that these things are related, and different people have different perspectives. So let's see if we can get a few images so that we can use that to buttress our point. We are actually looking for images, not necessarily the definition. So you see here, there's artificial intelligence. Within artificial intelligence, there is machine learning. Within machine learning, there is deep learning. In fact, for some people, deep learning and neural network are the same. What that means, if we are using that approach, is that neural network is part of machine learning, and machine learning is part of AI. I hope that makes sense. But if you now come to this other illustration, you will see that it looks as if AI is the umbrella name and that there are intersections here and there. But again, you see that there's no neural network. So it seems to us that neural network actually bears different names in some diagrams. And that name will be, okay, I'm trying to look forward. That name will be deep learning, okay? So somehow we can say that deep learning and neural network are so related. However, if you look at this fellow's diagram again, it's a bit different. It comes here to put AI here, has computer vision here. So in the end, we see that there's really no major conclusion. However, look at this man. It says deep learning and ANN are similar. I think I like this one. This is my favorite diagram. This one says that there is artificial intelligence. That is when your computer begins to behave or do tasks that are generally reserved for humans. Now, inside AI, there are a lot of fields, one of which is machine learning. That is the power behind AI. That is when your computer can, make predictions, learn patterns, learn machine learning without being explicitly programmed. It just learns from data. And then we are now saying within that machine learning, there are now aspects of machine that try to replicate the way the human brain is. And we are saying in the human brain, what dominates is neurons. So if you want to use your machine as though you are using the human brain, rather than saying biological neurons, you're talking about neural network. In summary, your naive Bayes and your logistic regression are machine learning methods. They are machine learning approaches. They are machine learning models. Okay? But neural network is a different category of what do we call them now? Of models. They talk about network. Remember that logistic classifier, naive Bayes classifier. Those two we have seen. And we said those classifiers are under supervised learning, if you remember. But now we are looking at a different category that has nothing to do really with supervised learning, unsupervised learning, and all those things that we talked about in our earlier classes. So this is another category of machine learning techniques, models, if you like, that trying to replicate what happens in the human brain. I don't know if I've answered you.
Yes, sir. Yes, sir. You have, sir. Thank you very much, sir.
All right. Thank you very much. So we go on, and then at time, I'll stop again and check if you are following. There's still going to be hands-on today and real programming. So we've seen inner layer input, inner layer processing, output layer, the prediction or the result. So how does this now happen? Okay, how does the neural network now perform its function? It relies on what we call the activation functions. That is where decisions are made. Let's try an example. Say I'm hungry right now. I'm not actually hungry now, okay? So, but because I just finished taking my meal. But assume I'm hungry. I can decide to eat after this class. Okay? I can also decide to take a break, and take my food. So I need to make a decision. So in making that decision, there needs to be an activity that will take place in my own brain that have neurons. In a similar way, your neural network also needs to have that ability to make decisions. So here we say that neurons must decide when to activate, when to fire. You know, sometimes when you are hungry, it's not only that you lack food in your system, it can also be psychological. I'll be surprised if a student is writing an exam and the problem that student has is hunger. But it's not as if hunger might not be there. But at that point, the neurons that are firing, the neurons that are active, the neurons that are activated are not the ones that have business with food. Suppose you are hungry, you don't have an exam, and there's a plate of food in front of you. Then there's a tendency for the neurons that will make you want to eat somebody else's food to be active. However, if you are disciplined, you might not have that temptation. Let's leave humans alone and come to computer. I believe that is a good illustration. So here, activation functions help networks make non-linear decisions. That's a serious matter, because it's not every time that humans just make decisions, wake up in the morning, take your bath, eat your breakfast, go to the office, do your work, return home, relax, take your dinner, and sleep. That's not how life is. There's so much of uncertainty. So the kind of decisions that we take or make are non-linear. That means they are not just straightforward from the word line. We now need to rely on certain neurons that fire at different times. For instance, I don't know if you have seen somebody in an air conditioner who continues to sweat. Why? Maybe there is apprehension about a particular deadline. That's for humans, but we need to bring that idea into the next things that I want to talk about. So first here, some of the common activation functions. We talked about this last time, the sigmoid function. This was the one we talked about when we were looking at logistic regression. Okay, so what this one does is it helps us to make binary output decision, whether between have a nap or not. Okay, you can even decide to smile or not. Okay, the decision to smile or not. So in the same way, your computer also has to do that. Okay, so it needs that function, the sigmoid function. Remember, we saw it in logistic regression, and we are saying, what kind of output do I give? Do I give 1 or 0? Do I say it's a spam or I say it's not a spam? That's what we're saying there. But that's not the only function that exists. There's also the ReLU function. Okay, so I think this is the linear. Let's check. Let's just check ReLU. Okay, I think something about rectilinear logic or whatever. So let's just confirm. So the ReLU is an activation function, but it is the, where are you now? The rectified linear unit. Okay, so I know that the L there is linear, but don't bother yourself about that. But we can read on. It's a function that's used in machine learning to introduce non-linearity into neural networks. So we also have the softmax. Prof talked about this when he was treating, I think, both naive Bayes and the logistic regression. We even saw it last time. So when you move from the binary classification capability of logistic regression and you want to upgrade to, for instance, to multi-class classification, then you change the activation function to a softmax function. So an example of where you can make decisions is in predicting whether an email is spam or not. So that's the target. And then you can now set a threshold to say that if at the end of the day, the probability value I get is higher than 0.5, then you can say spam. Otherwise, you predict that it's not spam. Don't forget that it's just a prediction that you are making. You might not be accurate. But like we said, these neural networks have a way of improving in their ability to predict correctly. Yeah, good. So remember that we talked about linear and non-linear. If we try to use a linear, okay, so what we can do to help us again is we can do feedforward and backpropagation. These are very important terminology in AI, machine learning, and all that. Feedforward and backpropagation. But I used to think that they are simple terms to know because one is forward and the other one is backward. Yeah, but let's just read and see that can help us. Okay, so feedforward refers to the process of data flowing through the network in one direction from input layer to output layer forward. While backpropagation is the algorithm used to adjust the network with by calculating the error between the predicted output and the actual target. What are we saying? If you go to our notes now, you now make so much sense to you, and you really like look at it. How our neural network works, step by step. Remember that there are 3 layers: inner layer, hidden layers, and outer layer, the outer layer. So the first thing is data goes into the input layer. For instance, there might be text in terms of words, the numbers, they go into that input layer. Okay. So the next step is that the neurons now assign weights to the input. The best way I can explain this is that, remember we talked about stop words in our last physical class. We talked about stop words and we saw a sentence like, this is a good movie, something like that, I can't remember. This is a good movie. And we said this and is are not really contributing that much. So in trying to use them for prediction, we drop them because they are just generic words. And we agreed that the keywords there would be good and movie. Okay, so the question now is, what probability do I assign to good and movie? How important are they? So which one of them is really supposed to look at, and to what degree? So that's what happens in assigning weights. Apple said that it's important for you to know that when we are writing the linear function, I don't know if you remember the linear function for the simple linear regression, and we said y is equal to beta naught plus beta 1x. I think you should remember that. And we were saying that beta naught and beta 1 are the estimates. So sometimes you can even call them weights. Attached to the inputs. I wish I could do what class are we now? We are in what class are we using now? We are using Google. Are we using Google Classroom? Let's see if we can get like a writing board or something. Okay, let me just go and do this whiteboard online. So let's just take an example where we have just one input and then write the normal linear expression for simple linear regression. So we said that y is equal to beta naught, which we call the intercept, and then we said plus beta 1, and then we added x. This is our weight. That's what we're saying. Assigning weight to the features. So that's what you see here. Each neuron assigns weight to the input. And then eventually we compute a prediction. This first 3 looks like the end of the process. Of course, looks like input layer, add weight to it, process in the middle, and then get your output. But sometimes, and in most cases, and that's how the learning takes place, if the prediction is wrong, backpropagation will fix it. That is, it will go back and repeat the cycle. So you have the more like the feed forward, okay? The input, the assignment of weight and processing, you compute a prediction, it doesn't work, goes back, and the cycle continues. So think of it like it's learning from mistakes. So you solved a particular question and you made a mistake and you asked to repeat it. And at the end of the day, you learn better. So what then is backpropagation? Simply put, is learning from mistakes. Okay, so you go back. Yeah, somebody's hand is up. Let's go back and find out. Yeah, your hand is up. Let's hear you. Did I just hear that sound? Was any hand up? Hold up.
Yes, sir. Edidion's hand was up. Maybe
Okay.
it was a mistake.
Edidion. Edidion. Hello, Edidion.
Yes.
Hello.
Good afternoon, sir.
Your hand was up. Was it deliberate or accident?
Yes. Concerning one of the steps, I want to ask ask a question for number 4. If the prediction is wrong, back proportion fix it. Does it mean that in this step, the computer is learning by error? Is it learning by error? Then after like reinforcement, after seeing the error, when goes back to correct it?
That's my question. Yeah, very correct. Very, very correct. So you can see it here. What you just said is in this note. Look at it. This back propagation is in 4 steps. It makes a prediction, compares it with the real answer. The difference between your prediction and your real answer is what we call the loss function. And you want this loss function to be small. Okay, if you are predicting that the word that follows should be million, and then what follows is billion. Okay, and somebody else says it is school. Okay, and you say it's billion. You say that billion to million, in a sense, are closer in terms of, you know, proximity, but billion and school are far apart. So the goal is to reduce the loss function to make sure that your prediction and real answer are very close. If you don't have this prediction that close, then you have to adjust the weight. If we have time, maybe next lecture, I will show you how the ReLU, for instance, how you can adjust the weight, and then you see how it begins to learn. Let's not go to that so that we don't get too tensed. So when we have learned enough and one is comfortable with you, then we'll go online and see how these things takes place in real sense. Okay, there are websites where you can experiment. But for now, what you need to know is that when it makes a prediction, it has to evaluate that prediction. And how does it do that evaluation? It checks the prediction against the real value. And if they are close, then it can attempt to want to improve it. But if it is far, it has no choice but to improve it. So what do we see in the third step? You adjust the weight of the neurons so that the next prediction will be better. And then you repeat until the model becomes accurate. This is another challenge altogether, because you need to know when to stop. In actual fact, you can begin to have better output, yes, improvement. But sometimes you have to ask yourself, am I getting as much improvement as the resources that I'm committing to this process of training my neural network? That's a serious matter that we'll talk about maybe in the second part of this, discussion. Because yes, you need to talk about efficiency. It's not only about having good predictions, but you must think of having good predictions at a minimal cost. And that's why the name loss function is very, useful, very appropriate. So when you see that you have a better prediction, you can try to adjust. Which example can I give you? Okay, so you go to the grocery and you want to buy, say, 1.5 kilo of potatoes. And then the guy selling it doesn't have a weight. Or rather, he has a weight, but he's unable to capture that 1.5. So what he does is he puts some of potatoes on the weighing balance and checks. If it is 1.7 or so, maybe he takes one off, he checks again, and then maybe he drops another one and brings a smaller one. Okay, so that kind of idea is what you do when you do back propagation, going back and repeating the process to see if you are learning, and then you achieve a better result. Let's go on. So an example is, first, your model predicts that the sentiment is negative, but upon review, it finds out that that particular sentiment is actually positive. So it has to go back propagation, and propagate it again. Okay, so you are feeding forward, and then you now go back and propagate. So what do? You adjust the weights of the network. That makes it to learn better, and then almost always will perform better. Okay, good. So what then are the challenges? Okay, so the first one is computational cost. If you are training a deep learning network, it takes a lot of time. Not just time, it takes a lot of computer, capacity. So your computer has a central processing unit. And the more you use your computer for performing this neural analysis, its capacity diminishes. It's like you have a car and you just bought it new, brand new, tear rubber. And you now say because it is new, you'll be traveling to Kaduna every day on these Nigeria bad roads. You'll be surprised that after 1 year, your car would have so much dropped in value. Why? Because you have you would have expended so much. Unlike somebody who bought the same brand new car, he lives inside UI, you buy the same day, and all he does is he goes from his house to his office. You'll be surprised after 3 years that you will not be able to compare the two cars on the average. Okay, good. So the other thing that is there, which is very, very important, you see this idea of overfitting. It's a major problem in machine learning and neural network and all of those paradigms of AI, deep learning. And the reason is that rather than your network, your learning to be memorizing the data, it's like a student who wants to write an exam and then teaches the question and then crams that question. They are crammed. He has already crammed how to write an informal letter. Maybe he just prepared and said, look, I'm going to write an informal letter. And the informal letter comes and he writes it and he does well. There's a tendency to think that the child has really done well, of course. But what has happened is that you have just committed it to memory, not that you have learned. What learning does is for you to be able to apply what you learned at level 1 to level 2. So in terms of machine learning, neural network, and all of that, by the time you spend time training or teaching your computer, it will now learn some other things that you perhaps did not teach it. That's the idea. So overfitting is when your neural network is performing well during training, and you are just like a footballer during training, scores 100 goals, and then he goes to the real match, and he doesn't know where the goalpost is, something like that. So it just memorizes the small training field where you people practice, and when you take him to another field, he's not able to perform. And lastly, when you have small weights, they can slow down the learning, and then they can even disappear. Okay, so there's also the problem of vanishing gradients. And the solutions that have been provided include using like the ReLU activation function. And I told you about, let's even try. Let's try something. So we'll say ReLU function graph. Let's do that. I wish I could get the video. So, okay. So, let's leave that. Let's keep it like I promised. So the thing there is, with this activation function, you are able to solve this problem of slow learning. So in short, when you use this as your activation function, the learning rate will be faster. Okay. Then the other thing is, you can then decide to solve the problem of the noise. What do we mean by that? So you want your neural network to learn the patterns. But apart from learning the patterns, it also learns some things that are not relevant, which we can call the noise. So maybe you want a child to go and watch a movie. And what you want the child to learn from that movie is morals, how to be kind. And then you leave that child without guidance and he watches the movie. Yes, that child might learn how to be morally upright, but would have learned some other things in that movie. So in the same way, when we are using neural network and we are using them for this kind of solutions, it's very important for us to be able to handle the noise, remove the noise, drop them out, so that your neural network will be learning the essential things, not memorizing everything, including what is irrelevant. And lastly, make sure you have a large data set, large and diverse sometimes, so that you know that you have learned, from diverse examples, you have a very large pool of data, and then you can generalize. You are going to see a demonstration of that when we begin to do the practical implementation of the embeddings. So the part 3 of our lecture is neural language model and word embeddings. At this point, we want to go back to class and ask what's happening in class. Class, what's up? Ganiat, who else? Favor, let's hear both of you. Ganiat and Favor, what do you feel? Ganiat.
Good evening, sir.
Favor, yes. How is it going?
It's going fine, sir. Your explanations are going well.
So what can you tell us from backpropagation?
That it's a model that learns from its mistakes. It learns from the errors and tries to perfect what it's doing.
That makes sense. Good. Yeah, you could have said it in a better way, but I still like what you said. All right. So this is now this is where our practical implementation starts. Neural networks are not only for language models. Okay. Neural networks are used in so many fields, particularly in the medical field. You can check that out on your own to know that, these neural networks are very vast. But because we are in this linguistics class, we now have to focus on the neural language models. That is the ones that are related to our field. And then we look at what word embeddings are and how we can practically implement them. So moving forward, we see that there are traditional models. And this was what Didion that was asking, or Cassava, somebody was asking now about naive Bayes. Okay, that was the guy with, what's that girl's name? Deborah. Yes, his name Lawal. I think I'm correct. So the traditional models that we have looked at, that is naive Bayes and the logistic regression, very important that we are mentioning them because both of them are probabilistic. They treat words as isolated tokens. What does that imply? It means that if we take, say, this sentence, I remember in one class, we were asking what would be the word that will follow love. I think somebody in that class said money. Okay, good. So this is like word prediction. Okay, you are predicting the next word. And you must have seen so many, generative AI models that help you to do these predictions. For instance, when you are typing, they give you word suggestions. So the question now that we can ask is, does love always follow money? Does I always follow love? Now you guys are the linguists. Which one is closer? I and love, and then love and money. Which one has a higher probability of having them side by side? Can somebody unmute and please tell us, from the linguistic perspective, which one of these words or pairs are closer in the sense of, if you check the entire corpus, or say maybe you get a library of books, maybe 5,000 books, and you just extract all the content in them. This is part A, and this is part B. Which one will have a higher probability of having the words succeed each other? Who wants to go?
Yes, sir.
Who is going? Is that Cassava? Okay,
Yes, sir.
two people have raised. Let's hear Cassava. I love, and then love money. which one will have a higher probability of having the two words close to each other?
Yes, sir. I think from linguistic perspective, it is I love, because
Okay, let's see.
I is
Good. Go on. Go on.
okay, because I is not a content word, is a pronoun. So, and pronouns are kind of limited. So there is probability that whenever we see love, we tend to want to add a pronoun, and the probability of choosing I is high than choosing money, because money is a content word, and we have millions, if not billions, of them that can fit in that frame.
Fantastic. Let's hear Deborah.
Okay, yes, sir. I was about to say the same thing also. My name is Kola
Okay.
Ole. Sorry, I'm joining from Enis.
Okay. Yeah.
Yes, so I wanted to say the same thing, because I love.
You agree? You agree?
Yes, I agree. Yes, I agree.
So now you're already getting the application of today's work. What then is it that brought me here? What brought me here was the fact that when you use naive Bayes and logistics and some other machine learning methods, what they do is they look at relationships between words, taking those words as isolated. It isolates those words. But when you use neural network can take I and love together, knowing that they come together most of the time. So in the real sense, neural network is an upgrade. By using neural language models, you have an upgrade. What do I mean by that? If you go to the notes, you will see that what the note says is that neural language models understand relationship between words. So while those ones will focus more, they take those words in isolation, neural language models. That's why they can give you a whole book. You just ask a question. Write me a story about what's happening at the Senate between Senator Natasha Dohan and Senate President Godswill Akpabio. If he can fetch information from the internet, he goes and fetches it and gives you a chapter. Why? Because he can do that connection. Okay, so let's look at an example. The traditional model, for instance, maybe naive Bayes, what does it do? It looks at king as a separate word, looks at queen as a separate word, and can understand each of them, but fails to really show the connection. So it sees them, not the way it sees them is not as in they are related. No. But for neural models, it's able to see how they are semantically close, in the sense that it understands that usually, because it understands even grammar, because it learns from existing literature. It's not as if it learns from heaven. It's what men have written. We are the ones who teach this computer to now become better than us. So by having neural networks, which could be a threat, quote unquote, we are partly responsible, because what it does is it learns from available information. So it has learned that king and queen have a close relationship. So that's the difference between traditional models and neural models. Moving forward, there is now a need to do what we call word embeddings. Why? Because, first of all, you have so many words. Secondly, there is even textual. And your computer doesn't really operate in that terrain. It operates with numbers, probabilities, and all of that. So you need now to, like a transformation. Okay?
Hello,
so
sir.
You see here, go on.
Yeah, please, sorry, because my network is not that friendly. Please, can you explain the difference between the traditional models and the neural language model once more, please?
Okay. So the traditional models like naive Bayes and logistic regression, they see words as distinct. They fail to relate words with other words. You are here now. If I tell you CNL 751, I think in your mind you should be thinking of CLN 708. because you know that it's Professor Lupu said that take the two courses. Okay, so if you are using the traditional models like a naive base, they see each of the words in a sentence in a corpus as unrelated. But when you now look at the language models, what they do is that they look at each of those words and try to find how close they are semantically in terms of usage. Okay, so it's not just merely synonyms, which could be, it could also be antonyms, it could be homonyms, it could just be usage. So when you say semantics, it might just be in the context of the use. So that's what we are saying. So the difference is when you use the neural models, they see relationships between words or among words. But when you use traditional models, they see words as isolated. Make sense?
Yeah, thank you, sir.
Brilliant. So when we now go to why do we need these embeddings? That's what I was talking about. I was saying, for instance, here it says if you use one hot encoding, which is basic form of encoding, there are improved versions. What does this do? It creates large but inefficient representation. So when you start learning neural networks and you start implementing them, one of the embeddings that you should start with is just one at a time. You encode one at a time. Okay, good. But there is also word embeddings. What this one does is it transforms the words into a vector. So what did we say about vectors? Vectors are selections of items that are similar. Okay, you take names, you take numbers, and you put them in, because of the language we are using here, in a bracket, then you say you have formed a vector. Therefore, if I look at 0.8, 0.8 is a scalar. But 0.8, 0.2, 0.4, and 0.7 now gives me a vector. So in terms of transformation, it's possible that the letter K is assigned 0.8. Are you with me? But however, in terms of comparison, what we will do is to look at these values here and compare them to the value below. You can see that 0.8 is close to 0.75, 0.2 is close to 0.22, 0.4 and 0.39 are close, 0.7 and 0.69 are close. So when you reach these values, you can conclude that, oh, there's a kind of relationship between king and queen. However, on the other hand, you can see the values. This can be in a multiple dimensional, field. In today's class, we are going to demonstrate with the two-dimensional area. I will talk about two-dimension. Don't let that terminology frighten you. So what we have now is with Apple. If you look at the value here, if you are trying to compare corresponding value, you see that Apple is at a different path. Where others are recording 0.8, 0.75, is recording 0.1. So we can conclude, although this is a very simplistic example, now imagine how this is going to be done when you are reading the whole paper. You know how you ask AI to summarize a paper, and you can imagine the amount of processing that goes on there. And sometimes it does that in less than a few seconds. What an amazing thing in AI. And we are just starting because we've not reached artificial general intelligence. This is just scratching the surface, scratching just the surface. All right. So we'll go on to say king and queen are close, but Apple is far, based on this word embeddings. So there are many examples of word embedding models. These are just three of them. I think we are going to focus on this Word2Vec. From the name, you can see what it does. It turns words to vectors. Okay? How does it learn? It learns words relationship from context. And I think I like learning from context, because we're in a world where people quote things out of context. Yes, you can say something, and then if you don't put the context, it will have a different meaning. So with Word2Vec, it has been trained so, designed in such a way that it's contextual. Wow. Then the other one is the GloVe, GLOVE, I don't know. It captures words from current pattern, and then there is the fast text, which handles some words. It's great for multilingual NLP. Good to know that the one we are using is the one that I'm a bit familiar with. So let's look at an example of the use of the Word2Vector. So this example is very intuitive. So you have a king, that is not a man, but a woman. That's a queen. So we can say a queen is a woman king, not a man king. I don't know if you get the logic there. So this is just the logic to show that that's how it's going to reason, and then conclude that king and queen are close. By the time you turn a king who is supposed to be a man, you remove the man in the king and put the woman there, then you should have a queen. Just the logic. So we want to implement word embeddings in Google Colab. So we could have implemented this in R, no doubt. But Prof chose to implement it in Python, and I became excited. So more like I appealed to him to allow me to this one. Okay, so the advantage that we have now is that for some of us, in my first class, we're able to introduce you to Google Colab. I know that not all of us were in that class, but so that we can save time, okay, and optimize this tutorial. I'll just do an introduction to Google Colab, and then we'll begin to demonstrate this. Otherwise, it will take away from our time, and there's still lots of things to cover. Let me go to the class and find out if that's a popular resolution. Let's go to, who do we go to now? Adedeji, what's your opinion? You and Ayofe, what do you feel? Were you have you used Google Colab before?
Yes, sir. No, sir. Well,
Which one are you saying? You said yes and no. So tell me the one to take.
No, I've not used Google Colab before, but I've used Anaconda.
Okay, good. As it is, you've used Anaconda. And when you use Anaconda, you must have used it at Jupyter Notebook or Jupyter Lab, right?
Yes, Jupyter Note.
Okay. Who was the other person that I called? There was somebody else that we mentioned. Ayofe? Ayofe? Wow. Okay, no problem. I tried to call Ayofe because I felt that Ayofe might not have been in our class when we showed you how to use Google Colab. So I'm going to take my time and try to show you, and then we will run this, try to explain as much as possible. There's so much going on in this material, and I hope we'll be able to cover it. So we finished the content of what we are dealing with. As we go on, between checking writing Python code. Because you are computational linguistics students, you need to take care of the computation there. And computation can be done by using computer languages. And there are so many computer languages that, vie for the first position. Python is one of those contending to be the go-to language for, this issue of linguistics, NLP, and all of that. So what we want to demonstrate here is word embedding. We also want to visualize it so that we can see how it looks and then discuss it. Like one of us said, you could do Python using other platforms. You can call them, IDE, Integrated Development Environment, or you can call them editors. Google Colab is our choice in this class because first, it's going to be online and it will save your work. And then secondly, you don't have to spend time downloading the software. So what do? We go to any browser, okay? And then click as if you want to check something online. Inside this search region, you write Google Colab. Once you start writing it, it will come up with Google Colab, which can also be known as Google Collaboratory. This Google Colab is going to come up as one of the first instances because it's really used, by the community. So I wish some of you are following, especially those who were not in our earlier class. So here we have Google Colab. You can just click on this particular link. I know the amazing thing. takes you here. But permit me to read this sentence or whatever you call it. These two sentences. Colab is a hosted Jupyter notebook. So for those of you that have downloaded Anaconda and you are using Jupyter Lab or Jupyter Notebook, this is hosted online. It requires no setup and it provides free access to computing resources such as graphic processing units and tensor processing units. It saves your system. It gives your system long life because you are not doing the processing on your system as it were. You are doing it in the cloud. You are doing it not necessarily on your system. Colab is especially well suited for machine learning, data science, and education. What else will you use if you are in this class? Apparently, that's what you will use. So when you are here, there are other things that you could look at, but we don't have much time. If you had a notebook before, you click on Open Notebook, Open Colab. And if you have not used it before, you might not have anyone. But for me, if you open mine, you will see that I have a lot, okay, because this is my favorite. I don't just use it for coding, I also use it for writing. Okay, I love it so much. So, and that's why I was appealing to Prof to allow me to do this. So we'll go to a new notebook, click on new notebook, and then you have a new notebook that is online. And then you name it. How do you name it? This untitled in your own might be untitled 1. But in my own case, it's untitled 32, which means that I must have opened 31 untitled files that exist inside my Google Drive. Remember, it's Google Colab, so it will be in your Google Drive. So I want to call this LING1 or LING. What topic are we doing? Okay, let me just call it neural NN. Neural network. Sometimes you hear ANN, artificial neural network. The A sometimes is redundant because neural networks are artificial. The reason for putting A there is that we have other types of neural network, convolutional neural network, recurrent neural network, and all of that. So why didn't I change this IPYNB? Because that's the extension. If I change it, it will affect this whole book. So what I'm going to do is, I want to now take the notes that we have in class. I will bring them into my Colab so that both the notes and the code will be in the same place. So I'm going to start from implementing word embeddings in Google Colab. So I can copy this implementing word embedding in Google Colab. I'll come here. Rather than going to code, I'll go to text. But you see that here I have code on top. Here I have text. The amazing thing about using Google Colab is that it has an inbuilt AI. In fact, it's linked to Gemini. So sometimes when you are even coding, it gives you suggestions. That should interest you. So if you want this line to be the first line, then you can push this arrow to the top. The good thing is that this class is being recorded, so you can watch and watch again. I'm doing this because I have friends here who have asked me that, oh, we are also using this tool in other courses. So I want to use the next 10-15 minutes to ensure that you can take advantage of this platform. But hopefully we'll cover the content for today. Okay, so I'm mindful of the content for today. So I want to copy that here. If I paste it here, oh, sorry, this is from something else that I was doing. So let me go back. So I want to copy implementing word embeddings in Google Colab. So I'll go here. I've copied that. I'll paste it. Why is it not giving me? Oh, okay, let me just write it. Wow. So if I write implementation of word embeddings, let me just leave it like that. This will be my output. But if I put hashtag it will give me a bigger size. So there are 3 possible hashtags. If you make it double hashtag, it will give you a smaller version. So I want the biggest. So now I have a note, the title of, this whole process is implementation of word embedding. So I can now go back to this material and copy this content. Copy. I'll come in here. I can actually paste on that without going to the next page. Why? This guy is just picking all of these things. Okay, let me not even do that anymore. So what am I saying? I'm just saying that I can copy these notes and take them there. So let's go on. So what do we want to do? We want to demonstrate word embeddings and visualize word embeddings in Google Colab. What are we going to do eventually? We'll demonstrate the use of the GenSim library for word embeddings. We'll go to the scikit-learn library package. This one is even a package. This is a serious package that contains so much and can do a lot of machine learning stuff for you. But here we are just using it for dimensionality reduction. And using the t-SNE. Okay, you don't have to know everything. But what it means is that instead of having so many features, so many possibilities, you want to take away those ones that are not contributing so much so that you can have few options. Okay, just like the idea of reducing the number of columns in your data sets. That's what it says. Okay, and then finally, you now have another library called the matplotlib. This library is used for plotting graphs. So what normally happens? Under normal circumstances, you should first install the packages. When we were using R, it's important for us to go back to R. Okay, so that we don't get it mixed up. You see that when we are using R, we normally do library. But if we don't have that library, go and say install packages. Let's look for one that's good. So here we say install packages, First step, if you don't have it already, then we now bring to the particular instance of our work. Like I gave in one class, I don't know whether it was this class. It's like buying, maybe a bag and then putting the bag in your wardrobe, or now using the bag for an outing. There's installation, good, but in the usage, the instance of usage, you must bring it with the library. In that same way, when it comes to Python, if there's a library that is not existing already, you need to install that library. But we use PIP to install. Where PIP is the Python installer, is the package for installing in Python. So if we look at PIP and we want to see what it means, it says here, sorry, PIP can mean many things. So we say PIP in Python is a package for installation. So we see that PIP is a package manager for Python that installs and manages Python packages. So in R, you say install packages, brackets, and then put the name of the package. But in Python, that's not all you do. You say PIP, and then you say install the name of the package. This is already telling me that it knows that this is what I want to install. Why is it saying this? Because I ran this notebook, I think yesterday. So it has it in its memory. And if you don't want it to install GenSim and you want it to install something else, then you can as well write it there. But if it was on Jupyter Notebook, that means if we're using Anaconda, this would suffice. But if you are using Google Colab, then you need to add the exclamation mark. What are we saying? If you are using maybe Visual Studio Code, somebody mentioned Visual Studio Code in class, or maybe Sublime Text, or even Jupyter Lab, that Anaconda Spider environment, you can use pip install in GC. But if you are using Google Colab, then there's a need to put that exclamation mark. So when you now want to run, you press this play button. It will first connect to the internet. then it will save in the cloud. So watch this connecting. Once it marks this correct, it means that it has finished processing. What has this done? It has, wow. It has taken care of Genzim. It says NumPy is already there, SciPy, Scientific Python. It says all these things are already there. Once this gives you this tick, it means that that line of code is okay. All right, let's hope that we are making progress. If we go back to our notebook and see what is put there, we see that it says open Google Colab, create a new notebook, which is what we have done. And then we'll move forward. I want to install required libraries. Can you see exclamation mark here? Because we are using Colab. It says install Genzim. I might choose not to install scikit-learn and matplotlib. You ask me why? Because I know that scikit-learn and matplotlib are already in Colab. But it's wrong for you to assume at times. So two ways to do this. You can install Genzim and then install the other ones after. So I can actually do next line, pip install matplotlib. Okay, you can see it's already saying install Python FHTN. That's another package that is useful for language models, useful for neural modeling. This neural language model that we are talking about, this is another package. It already knows, it has an idea that, oh, this fellow is trying to run something in the area of machine translation, sentiment analysis, topic modeling, and all those things that have to do with language. So that's what you see there. However, we are not going to use that approach. We can now write the libraries that we want. We have the scikit-learn. That scikit-learn is the scientific kit. So that's when you are doing proper science. I'm not saying linguistics is not science, but you know what I'm talking about. Maybe physics, geography, and all that. Then this library becomes very important. Then you leave space and then do matplotlib. This one is for graphs. So I can now run this. But there's waste of resources when I run this again and again. So what I normally do is, after run, I'm going to run it though. I won't stop you from seeing it. Once you run matplotlib, it brings in many other things. You can see that it now says that there are so many requirements that have been satisfied by just using these three libraries. Like we did when we were looking at R. Yes, we did that. When we were looking at R, we said that after installing for the first time, you can comment out these two installations so that you don't waste data, you don't waste resources. So that next time, since the library is already there, the package is already there, you can only call it. Okay, so in the same way, once we have run this, we can use hashtag to block off this code. So if I run, it will not be activated. So going back to where are we now? We are here now, so we are from this line. Let me go back to the class. Let's see if we are flowing. Is there anybody who is replicating this code? Anybody?
Yes, sir.
You've not written many lines. Good. And are you okay so far?
Yes, sir.
Brilliant. So if I can get somebody who is doing it, it means that the others will be able to do it. So now we want to generate word embeddings. So we will use the Genzim library to train a simple Word2Vec model on a small set of sentences. So I wish we could type this whole stuff. Okay, this whole thing. But I wouldn't have enough time. So I'll first copy this portion from here to this point. I'll paste it and then explain some of the lines so if you click on this text, you can write notes and then you can cancel it. But if you click on code, then you can impute code. What is happening in this code? In this first line, we are going to the Genzim package. We want to pick a model And the model that we want to import is the Word2Vec. That's what's happening in that first line. So it's like, go and look for Word2Vec from the Jensen package. But no, remember that it's a model. So when you have dots, we call that a module, okay, or a method. So this is an example sentence, or example of 5 sentences. These 5 sentences have been cast into a list. Let me explain. So if I have a list, let me say I have a list. In Python, lists are represented with square brackets, and they are separated by numbers. So this is a list. In this list, we have 3 items. But it is possible to have a list inside the list. So if I increase this, you can see here that we have one outer bracket and it ends here. But inside that bracket, we have the following elements: 1, 2, 3. And then the 4th element is also a list. So that's what you have here. You have the outer bracket, which is a list, but inside of them, you now have each of these also containing a list. This is what you call a nested list. List inside list. So moving forward, you are supposed to now, begin to ask yourself from each of these sentences, what are the words that are very special. So let's go on. So we have what I call a nested list. The item in the first position, which is position 0, now contains the following words. When you use letters like in R, use double quotes or single quote, but make sure you are consistent. So the first sentence is, the cat sits on the mat. The second sentence is, the dog plays with the tail. The third one is, birds sing in the trees. And that's how you have those 5 sentences. If, for instance, I say print bracket sentences, and we run that, it says no, you cannot print sentences. And then we want to know why. I'm just curious. So we'll go, say sentences is not defined because I've not run this line of code. So this introduces us to something very interesting that we talked about in R, but the first time of talking about it in Python. When you run a line of code and you see an error message, I'll be scared. I don't like seeing error messages. That's the truth. But with time, you see that even the error messages gives you a clue of where the problem lies. In my own example, it says that it has not seen sentences before. So I now realize that I had not run that line of code. And the way Python executes, it executes cell by cell. It's very linear. It just goes and picks it. So when I now say print sentences, it now prints the sentences for me. So what I'm going to do is I'm going to hide this output because it's not actually part of the code that we are looking at. But like I said, the time I've allotted for these basics is as a lapse. So let's continue with our material. Now, after you have imported the Word2Vec, model from the Jensen package, the next thing is to now train it. So what I'm going to do is I'm going to copy these 2 lines. Then I'll go into my code and then paste them here. And then we'll begin to discuss them. Don't forget that we have agreed that there is training and there's testing. You train your model so that when your model sees fresh data, the pattern that it has learned from the training, you can now apply it. So what do? Remember that we are trying to, implement the word embeddings. Where are we? We want to train our model. So we give it a name, model. can write any name there. Okay, it doesn't have to be that name. So this is an object or a variable. You now assign that variable, unlike R, where you can use less than and dash, or equal to. In Python, you use equal to strictly. Then we get the Word2Vec function. I told you in R that once you see any word and there's a bracket in front of it, it's called a function. Now, when you pick that function, you can relax and learn. What does this function do? Okay, so from what you see on the screen, you can see that that function has several information in it. Okay, so you define a function and check what is in it. Sentences, you specify. Is it from a particular place? What corpus is it from? Then what's the size of the vector you want? And some other details. You can see that the details in this example that we are looking at is not that much compared to what we have in this sample. So what we have is we have picked a few of those parameters or arguments. The things here are called arguments. So what I will expect you to do is to go and find out on your own. What does window mean? Why is it 5? Then minimum count, why 1? Why do we have workers equal to 4? But I can begin to give you suggestions by just showing you these sentences and you checking what you have there. But go on your own and find out the real meanings of that. But they are not things you should bother yourself about. It is the implementation that we need. So by the time you run this line separate, let me run that line separate. If you run that line separately, what you would have done is that you would have, created that model. And then when you now go to the next line and you do this, you would have transformed that model into a word vector. What you want is words, sentences. You want to turn the sentences into a vector. Let's try something. Let's print. Can you imagine? The guy already knows that's what I want to say. So when I print word_vector, it says that the size of my vector is 100 and there are 19 keys. I wonder if this will be 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's not true. Okay, 12. That's not true. That doesn't fit that. So you can always investigate this stuff and find out what they mean. So going back to our notes, what are we saying? This is how you define your model specification. You generate word embeddings. You've converted what ordinarily was in the form of text to a vector. All right. Remember that we're looking at how to solve a few problems. Let's go back to see what we're looking at. We're looking at how to solve a few problems, and we said something about reducing the number of parameters, or maybe what we talked about was using scikit-learn for dimensionality reduction, reducing the number of dimensions. So we are done with the JSON library for word embeddings. Now we want to do reduction in the dimensionality. So if we scroll down and then we check our code, it says we'll use the t-SNE to reduce the word embeddings from 100 dimensions to 2 dimensions. The reason for 2 dimensions is so that you can capture the graph. 100 dimensions, okay, so 2 dimensions is horizontal axis and vertical axis. 3 dimensions is horizontal axis, vertical axis, and diagonal. Imagine what 100 dimensions will be. You cannot capture that. So we need to look for how to transform from 100 dimensions to 2 dimensions. And that's why we need this library. And where are we going to get that library from? We are going to get it from Remember I said that the sklearn package is the scientific kit. So S is scientific, K is kit. And I said it's for heavy science, maybe like astrophysics, maybe like neurobiology, those very pure sciences. So what we are going to do here is we want to get this t-SNE, but we can't get t-SNE except we go to CLN. So that's why we go from CLN and get t-SNE, and then we import NumPy. NumPy is another library that helps us to do numerical computation. So sometimes we say NumPy means numerical Python. Okay, good. So when we take all of this, let's first copy this, put it in our instance and see what it looks like. So run this and put everything here. And then what I want to do is I want to break this into different cells. The reason is that it makes it tidier. We can see implementation in stages. However, see that this vectors is giving me an error. It's giving me an error because it doesn't know what vectors is. So we this will not be the last line. It has to know what vectors is. It has to understand vectors in this previous line. So once I cut off that previous line, it then complains that I've not seen these vectors before. That's another beautiful thing about using Google Colab. Of course, I know Jupyter Notebook does that too. So where are we now? Yeah, we still have a lot of time. Okay, so if I'm running too fast, that's very unfair. But if I'm slow, don't worry, we have lots of time. So we have seen, the structure of these printboard vectors. Because they are vectors, they are not, you just need them to carry out, to find solution. Like a mosquito that carries malaria from one person to another. Even though it has done something that is harmful, or in economics, we say it's the economic importance. Okay, so that importance might be a negative implication. So in this sense, that vector might not be something that we can really visualize in that sense, but it does a lot of things behind the scene, under the hood. So in this line, what you are doing is you are importing t-SNE, but not directly from CLN. And here you are importing NumPy, and you are changing NumPy to NP. No longer NumPy. From now on, we will write NumPy, we write NP. So anywhere you see NP from now on, it's actually NumPy. For instance, in this next line, you can see np.array. So the question is, why do we have to go through that? Because we want the structure of your text, those sentences, to now form an array. And the library that can do that for us is NumPy. So when we bring that library in, then we are able to, enjoy that part. Here, a lot of things are happening, okay? A bit of programming stuff are happening here. For instance, we have a for loop here, okay, for word in words. So the words will be the entire corpus, and the word will be a single word, okay? So we want to get the words and their corresponding vectors. So each word now has a number assigned to it. If you have forgotten, remember king, queen, and the apples. And we say king and queen are close together because of the structure of representation. So here we have words in the form of a list. Remember, we had a list, that list that we called a nested list. So that's what is happening here. You are creating the bag of words, if you like, and then you are now transforming the words, each word inside the words. You are transforming them from mere words to vectors, and you want to put them in an array, and you want to name them vectors. That's what's happening here. So when you run these two lines of code, you would have created two things. One is words, and the other one, vectors. What is the goal of this? We want to reduce the dimension. Where do we want to reduce the dimension from? We want to reduce the dimension from 100 to 2. Okay, because if you recall, at the beginning, when we were making our specification, we said we had a size that was that huge. So if we come here and we run, so we create an object called t-SNE, okay, using this t-test, okay? Let's even confirm that. So we say what is the full meaning of t-SNE. Okay, so it's an evaluation metric though. So we say t-SNE stands for T-distributed stochastic neighbor embeddings. Forget that big name. The most important thing is T-distributed. It follows the T-distribution, which is a machine learning technique used to visualize high-dimensional data by reducing it to a lower dimension, typically 2 or 3 dimensions. That's what's happening there. Okay, so we have brought this into our space, and we now want to, so there's a transformation that is happening here. Transformation of your otherwise multi-dimensional vector to a 2-dimensional vector because you have used your t-SNE to transform it. Fantastic. So if you run that line of, I almost said praise the Lord, but I've even said it. So when you do that, you've created 2 more objects. And what's next? The next thing is to pause and ask us what's happening. Let me go back to the class. Who hasn't spoken? Robert, Robert. Robert has left. Cassava. Cassava.
Yes, sir. I'm here, sir.
Alpha, is it getting hot or you're okay?
Yes, sir.
Are you okay?
Yes, I'm fine. I'm following and I'm trying to run some.
Oh, yeah. You're also running it. Are you successful?
You've gone far beyond where I am.
But
I'm following.
But you can watch the video later, right?
Yes, sir.
Okay, fantastic. So we now want to visualize. We now want to plot it. So let me copy this code also and tell you what is happening in the code. Okay? So we'll copy all of this, bring it to our own file, and I want to explain. I want to leave all of this in the same. Okay, well, let me just import matplotlib. Let me make this to be separate. I don't like the line that I'm seeing. I'm seeing a line that is not so impressive. So I'll put import here. I'll run this, and then I'll cancel this stuff. Okay, so I see what happened. So first, we have imported matplotlib.py plot. What we have done is we have reduced this whole matplotlib.py plot to just plt. So when I come here, I wouldn't have to write matplotlib. I'll just write plt. So let's start from the top. We want to plot a 2D word embedding. We want to have like a graph, and then want to see all those words and where they are located. Okay, where their weights takes them to. Then we want the size of where we are going to draw our graph to have a length of 10 units and a breadth of 8 units. That's what's happening in that line. We want a length of 10 units and a breadth of 8 units. So if you want it to be bigger, you increase those numbers. What's happening here is that you actually want it to be a scatter plot. What do you mean by a scatter plot? You want it to just pick points at whatever locations that they are at. You don't want to connect them with a line. You are not drawing bars. You are not drawing a circle. You are just picking those words and you want them to be in particular locations. That's why you call them a scatter. You want it to be a 2-dimensional vector. Okay? You want to pick the whole row, all the rows, beginning with column 1. And then you want to now pick everything again, picking column 2. And you have chosen to use the color blue for aesthetics so that that color will show. So that's what is happening in these lines of code here. So I can actually copy this add it to a fresh cell, run it, and this is one way to run code. When you run code like this, you begin to understand it layer by layer. Okay, it's called sometimes abstraction. Can you see what this gives us? Are what? The scatter plots. I'm glad you have seen this. But I'm going to copy this whole thing, and then I'll return it to the next line. Because by the time I marry that with the remaining, the many lines of code, it will do much more. What do we want to do here? We want to annotate the point with corresponding words. So instead of having these blue dots, are you with me? We are now going to have words there. All these words that you have here, D, cat, six, and all that, they are going to be the ones that replace dots. What are we saying? We are saying that because you want to go through the entire list, you now have to use what we call a loop. Go around. You want to check every word. Go from first sentence to the next sentence to the next sentence. So here you are introducing a for loop, and you are saying for I can be anything, for anything, for X, for anything, but not that whatever you put here is what you are going to put in these other lines. So for Y, comma, what in enumerate words, what it means is pick each word in the whole enumeration. Then when you use a for loop and you put colon, this next line must be indented, meaning that you must use tab to move it forward 4 steps. If you don't use tab, you can use the space bar 4 times. Space bar 1, space bar 2, space bar 3, space bar 4. But I don't like using space bar. I love using tab. So use tab, because sometimes your space bar 1 might become 2. So what are we doing here? We want to annotate. We want to, as a linguist now, we want to write on those dots for each word. We want it to be, a 2-dimensional vector. Don't bother yourself about spelling things here so that you don't get discouraged. So the rest is about labeling. The title, what you have at the top of the graph will be t-SNE visualization for word embeddings. Then on the horizontal axis, you have dimension 1. On the vertical axis, you have dimension 2. And this one now says, show me the plots. So if I run this now, you have a new plot, but the plots now will now be annotated. So it means that swim is here. In terms of the dimension, let me try to reduce this. Okay, good. So in terms of the dimension, in dimension 2, you can see that swim, sun, fish, cat seem to be close together. I don't know. Sing, sit, trees. Can anybody make sense of this thing? Can you tell us from the linguistic point of view? I can tell you from the computational point of view that these words that are close are contextually similar. Context, don't forget, contextually. And that this, like math, is so far from swim. But maybe we can talk about that as we continue looking at the document. The document will definitely help us so that we save time. So interpretation of the visualization. So we want to check, what we are going to have eventually in the embeddings. It says that the t-SNE plots represent a 2D visualization of high-dimensional word embeddings where similar words appear closer together in space. So with that small example that we have, we're able to see words that are close in shape in terms of, semantics. I don't know if you know what they call a word cloud. Okay, so it's a diagram, like a chart that shows words that the frequency to which words appear in a document. So there's a lot happening here. And we just have to make sure we finish this document. So if we go on, it says that we can observe clusters and word relationships. For instance, in terms of semantic similarity, some fish, cat, and in are positioned close together, suggesting they are related in context. Some fish, cat, and in. Sun, fish, cat, and in. They are closely related. I don't know, you guys will let us know that. Dog, birds, shines brightly. That sounds like a poem. Dog, birds, shines brightly. You know, you are the guys that know, you bring in your knowledge of linguistics. So this is about semantic similarity. But beyond that, there's also verb association. And that's why maybe swim is at the top. He says here, maybe because it has a distinct meaning compared to other words. So what I see from here is a situation whereby by the time you look at other words in this, bag, swim maybe appears unique. I would have wondered that ocean would be close to swim or close to fish. I don't know. You guys know. So we just go on. So we have play, sings, and sits are positioned separately. I would have thought play, when you are playing, you are singing. But it doesn't necessarily work like that. So where is play? See play. Where is sing? See sing. They are far apart. So this gives you an example of the description of the plot. That's what I wanted to show you. Then prepositional articles with the ocean are grouped together, showing their common concurrence in language. That means maybe they occur together. I don't know. You are the one that knows this grammar. So you are going to make so much sense of this because of your domain expertise. But I'm just able to show you, a few things on how to compute that plot. So you see that, like we said in some of our earlier classes, if not all, that even though you don't have that background of mathematics, there's a role for you to play. There's the need in AI, we are needed. You can help to explain what is happening in the results that we see. So don't always think that machine learning, AI, and all that is only meant for people who have a strong background in math. It's true that that could give them an advantage, but it's true that there are other ways that you can help. Because in this world of science now, it's a collaborative world where everybody has a role to something to contribute. Ghanaians, let's go.
Yes, sir. I have been following the demonstration. So, but to now uh, plot the graph, this is what I have, sir.
Yes,
I'm
so
coming, sir.
yes. You want to do what? Hello. Ghanaians, don't share your screen. Don't share your screen. Don't worry. Don't worry. Don't share your screen. We might not have time to check your output now, but you can take a screenshot and send to me privately. Okay, let's do that. But I get your point.
Okay.
I think what you were saying was that when you try to implement it, you were not getting exactly what I got. Yes, possible, because again, we are all also learning. So since we are learning, we are allowed to make mistakes and also learn, like the neural network is also learning. That's backpropagation. Am I correct? Backpropagation. So what does this tell us about the word embeddings? The model has captured meaningful word relationship. What did it do? Words with similar meanings or common context like ocean and wheat are close. Words with different meaning like trees and swim are further apart. Some words are more distinct than others. For instance, swim and sing, they are positioned far from most other words, suggesting they are less contextually related to the rest of the vocabulary. So those ones that are far apart do not really have much relationship with the entire vocabulary. Maybe taking all of them together. I think somebody is also raising hands. Let me check. Udo, go. Udo,
Yes, sir.
go on.
Okay, I don't know if there's anybody that has any opinion on this word relationship, because the output to me, I don't really know. Maybe it's really related by the computer, but for me, I don't really see a relationship between a dog, bird, and shines, and
Okay,
also
so
ocean.
let me tell you what has happened. I'm happy
Okay.
that you mentioned that. So if you remember when we were doing this lecture, we said it's better to have a large data set. Do you remember?
Yeah.
We also talked about overfitting problem. This corpus that we have used is too small to train this model. Okay? It has not gotten enough. Don't forget that what is learning is just learning from 6 sentences. It's just learning from the sentences that you have provided. And the sentences might have been provided arbitrarily, not necessarily copied from a complete document. Maybe you didn't realize that. Let me share the notes with you. And that's a very good question. If we go back, and this has nothing to do with everybody in the class. These are the sentences that we have written. The cat sits on the mat. The dog plays with the ball. Birds sing in the trees. We are the ones that have brought these words. And first of all, there are even 5 sentences. There are too few. And, you know, before you can get a model that will learn, you learn from billions of information, literally billions. So this is just 5. So what you are seeing, we are all seeing it, because it's just a simple demonstration of how it works. Does that help your concern?
Okay. I've got that, sir. Thank you. I also have another question, sir.
No, before you go, hold on. Before you go to the other question, tell me what did you get?
It's from the explanation I've got that that the data set we use in training the model is too small, and
Correct. Correct.
and that
Correct.
could cause kind of inaccuracy. Inaccuracy.
Correct.
Inaccuracy.
Okay, go to your second. Correct. Go to your second question.
Okay, I don't know. I'm almost afraid though, if we will encounter this level of coding, programming in in the course of our examination or assessment, because the line of the code, I'm still looking at it like this, and I'm almost terrified. Thank you, sir.
Please don't be terrified. No matter how difficult anything is, if you practice it again and again, you will master it. Yes, somebody else is raising hands. Yes, go on. Somebody else is raising hands. Okay, maybe that was accidental. So, Udo, don't be terrified. Okay, this might be your first time seeing these lines of code, and you want to take it in at once. That will be very unfair on people who use years to learn these things. So the much that you can retain, make sure you understand it. Worry about exam when we are close to exam. So when we are close to exam, we'll talk about exam. Right now, try to grasp the concept, the concepts, okay? Udo, pray with fear. There's no fear in all of this. It could be terrifying, but don't allow it to intimidate you. Can I go on, class? So,
Yes, sir.
yeah, in order to answer Udo's question more formally, we now want to answer the question more formally. Watch what we are going to see in the next slide. So in the next slide, we'll see possible improvements. What is the first possible improvement? Increase data set size. Because more of the training purpose could improve embeddings. So we've seen that weakness in the embeddings, and we have seen that it's impossible to have an improvement. Then we can fine-tune. This fine-tuning, upper parameter tuning is another topic on its own. But what it means is that through some adjustments, we can now have better cost acceleration. So, like I said, upper parameter tuning is a different concept altogether. Then we can use models that have been trained We take those models into our own instance, and it helps us to provide a better embedding. How does that work? Let's say you want to translate from French to English, and you find that it's easy. But you know that if you want to translate from English to EFIC, it might be difficult. But you already have like the structure, like the code, like the solution. Yeah, I like that word. Like the solution, a pre-trained that has been trained before. A ready-made solution, okay, that has been used to translate from English to French. It's possible to now bring in that model, that existing one that has been trained, and introduce it into your solution. Now you want to translate from English to EFIC, it can help to improve your work. And that's the whole idea about generative pre-trained models. So when you hear GPT, they are models that are already trained for a particular task. You can now bring those models and they can now generate the kind of result that you're expecting. I hope that makes sense. Watch this video again to make sense to you. So it provides better embedding. So like our brother was saying, he was wondering that thing was not making sense to him. And he wondered, why is it to me? Who can save me? And then we said, no. You can improve by first increasing data sets, doing hyperparameter training, and using pre-trained models. So this brings us to the conclusion of what we have today. So what have we done? We have seen that similar words appear closer together, even though in our demonstration it was not that obvious, and we know why. We have seen that eventually unrelated words are far apart. What it means is that when you now want to implement this for a more robust output, first get enough data. Then the t-SNE plot effectively visualizes word embeddings, showing how words relate to each other in context. Remember when I was speaking to the slide on the visualization, I was saying something like, I don't know, okay? I was saying like, oh, this relationship, I don't know. But you see, the truth of the matter is, even though I knew, I really did not know, but I also know that I was learning from that small data set. So we need to increase the data set. So the cluster suggests that the model has successfully learned semantic and syntactic similarity among words. So you now go to, where do you go to? Go to this material, okay? And then you need to prepare for the next steps. What are we going to be looking at? Neural networks are, okay, this is summary. Neural networks are great for text classification and NLP stuff. Backpropagation, sorry, please. Propagation helps neural networks learn from mistakes. Remember, learning from error. Word embeddings improve word relationships embedding. And then you can now replicate this in R, okay? Train and visualize the word embedding. So it's possible that maybe Prof will speak to this maybe in the next class. I don't yet know the ideas that he has in mind. Okay, but we have used Python today. So your hands-on activity is try to go and check this. Okay, so I can copy this. Maybe you can always check this yourself. So what do? You train a Word2Vec on the next data set. You get a new data set. Now a real data set, maybe from a novel or even from the Bible. Because I can tell you, many of the language translation models use the Bible for translation. Apologies to our brethren. Because I used to say, and I'm glad that it has been confirmed somehow. I used to tell people who have challenges with learning English. Okay, I tell them, read your Bible over and over again, not necessarily King James. There are only few words that are not in that Bible. I'm not talking about spiritual whatever. I'm just talking about text. Okay, so many models use the Bible for training now. So visualize embeddings using t-SNE, analyze the similarity between words, and then if you can do this, and if you can go to use another word embedding rather than Word2Vec, you can use another one. That would be interesting. So these are extras. If you want to use a pre-trained word Word2Vec model instead of training from scratch. You can use the pre-trained word vector provided by libraries like Genzy. One popular example is the Google News Word2Vec model, which is trained on the corpus of Google News articles. Can you imagine using Google News articles to train the model? Because again, if you can use Google News articles over the last 30 years, yeah, you would have captured nearly all the words. That's why when you read a lot of stuff and you read diverse, materials, your vocabulary improves. Same thing with your machine, your computer. If you expose it to, a lot of, content, it learns a lot. It sees the structure. It checks the semantics, the syntactic, and relationships. It does all that for you because it's so smart to get that. So the code demonstrates word embedding and visualizes word embedding in Google Colab using Word2Vec, a prepared model. So how do you do that? So you go, this could be an assignment for you. You open Word2Vec. I've done this. Create a new notebook. Get the same libraries like we got before. Can you see? Same libraries. But now you are going to get from, Google News. That is a pre-trained model. Or sometimes you will need an API key, okay? An application package, interface that will help you to access it. Sometimes you may not need that. In reality, I actually ran this. I ran this and how do I get there now? Let me just see if I can get there. I ran these lines of code. Yeah. I ran this and then did the hands-on, and I have my output too. So I think I can show you my output. This will take time and it will take a lot of memory. Okay. So this code now, this import using the download as API. Okay, that's what will help you to fetch from that website, that Google News website. That will take some time and some data and some memory. Okay, so you can do that. Just take that and mine train successfully. I wouldn't want to do that again, And then at the end of the day, I think I got an output. So I don't know. Again, I don't know. It's also small. Why is this small? We have only taken king, queen, man, woman, cat, dog, computer, car, tree, and apple. What can we get out of that? Very little. On that note, I want to say thank you very much. God bless you.
Thank you, sir.
Yeah, God bless you.
Thank you,
Ididion,
sir.
go on, raise your hand and make your point. Thank you very much.
Thank you, sir.
Yeah, thank you very much. God bless you.
Okay.
Ididion.
Thank you. Yes. Thank you, sir. Thank you for the lectures and the explanation. But on these activities, as we are going to do, there's some lines of code are missing in the slide. So I don't know if you can send.
No, don't worry. So what you do is you highlight everything and pick it and paste it. You'll get it. Don't try to code and replace and how do I say it? Don't try to look at it and copy the code. Highlight it and then copy, paste it on your stuff. Okay, but if you, but I know you guys. So what I can do is let me download the one that I ran and works. I think that's what you're saying. You did it.
Yes, sir.
Okay, so let me go to our classroom. What's the name of our classroom again? Our classroom is what now? What's the name of our classroom? CLN, something like that. Okay, so we'll go to that classroom. I mean, that's WhatsApp. What did I? Okay, so I've put that task there. Okay, let me down. I'll put that task there. I can now go to my downloads. We are leaving this place in the next few seconds. So, ladies and gentlemen, I've put the task there, and I've also put my own code that I ran, the complete code. On that, good evening, everybody. God bless you.
Okay, thank you, sir. Thank you very much.
Yeah. Good night, everybody. Good night.